Okay, so good morning to everybody. Thank you for coming. It's a great pleasure to present today an quite old friend. He's Leonardo Civale, and I will just make a summary of his life and his relationship with the ICMAB. Today we were just thinking when he was here as a postdoc, and it is more than 30 years ago. So let's say that Teresa, myself, and Leo, we are sons of the high temperature superconductors. All of us, we started our scientific career with the discovery of high temperature superconductors. And I'm sure that if 30 years ago we could think about the possibility of talking about the use of high temperature superconductors in fusion, we were mad. So it's clear that it was not the case. So Leonardo is, as many scientists from Argentina, son of Bariloche. Bariloche, for the young people that you don't know, is very, very in the south of Argentina. It's an isolated place where you can only do science, and they do very nice science. And so he prepared the PhD there. We were always strongly correlated with the group of Bariloche because the founder of the low temperature group there was Paco de la Cruz, who was actually born in Barcelona, but he left Spain at a time where many people left, so after the Civil War, and he started a very nice, worldwide famous group in low temperature physics in Bariloche. And there, a lot of people was trained, very well trained, and now they are spread all around the world. And Leonardo prepared the PhD there. He came from Buenos Aires, then he moved to Bariloche. And after that, he started his career, scientific career around the world. I would say that after the thesis, when the HTS appeared, we learned quite a lot about physics, vortices, and everything in single crystals or very fundamental materials. Then he moved to IBM in Georgetown in the US, where he made a postdoc with one of the most famous physicists, Alex Malozemov. At that time, he had the idea, because he was already quite a lot of experts on vortex spinning, and he had the idea to irradiate single crystals with protons, ions, and so on. At that time, with the idea to improve the properties. And now, as you will see here, this is Dr. Jekyll and Mr. Hyde. So sometimes it improves, sometimes it goes worse. And for fusion, it's essential to understand how the defects that you could generate with irradiation modify the superconducting properties. And I would say that the most celebrated papers in the ion irradiation and so on was made by Leonardo when he was an IBM. After the IBM, he came back to Argentina. It was not very nice times at that time, the country, but he continued the low temperature physics group in Bariloche, and around 2000, I think, 2000, 2002, he moved again to US, and that time to Los Alamos National Laboratory, which is probably those of you who have seen the film of Oppenheimer, is the place where many scientific things happen. And in particular, the superconducting, high temperature superconductors was one of the more famous places. And he became the leader of the low temperature group in Los Alamos. This was already the time where now the celebrated coated conductors already exist. And so it was really necessary to have somebody with a good knowledge of the physics of the high temperature superconductors in order to make what it was at that time what we call a solution, which was the high temperature superconductors, to find the right problem. Okay, so we had very nice materials, but it was still not possible to industrialize these materials because it was too expensive, the performance was not good enough, and so on. And so during 20 years, we have been in Los Alamos, in Barcelona, and many other places in the world, improving the properties of these materials. And now the coated conductors is really a product where in the world we already produce 5,000 kilometers per year or something like this of coated conductors. And that's why now we have already the problem. The problem is fusion, and we need the coated conductors, the high temperature superconductors. and Leonardo will try to make in 1 hour or 45 minutes a summary of the situation, why the fusion requires the high temperature superconductors, and why the radiation problems are essential. So what it was at the beginning, a fundamental problem to understand the relationship between defects and vortices, now it becomes something essential because actually the superconductors magnets in the fusion are submitted some irradiation in fusion, and so we need to understand how to solve this problem. And hopefully in not many years, we will have a fusion reactor working with the high temperature superconductors. In any case, now all around the world, the fusion reactors have completely changed, and nobody will do a fusion system without the HTS. And so many initiatives around the world are now pushing the fusion, and we believe, we are convinced that the fusion is a new opportunity for transforming these materials in a real solution. Thank you, Leo. It's a big pleasure to see. He was here, sorry, forgetting. He was here for sabbatical, I think 1 month, I think.
I want to mention. Yes.
So please, go ahead.
So yeah, thank you very much. Thank you very much. Yeah, lots of things that I wanted to say. He mentioned, I'm impressed of how many good things you said. Thank you. I have to hire you as my PR person, really. It sounded impressive. Good morning, everybody. I'm really glad to be here. Thank you for coming. As Xavier was saying, I came to Barcelona for the first time in January 1993. And I spent 1 month here at the Institute working with them. And I immediately fell in love with the city. So I enjoy each time that I have the opportunity to come back, like today. So thank you, Teresa. Thank you, Xavier, for the invitation, for having me here. With my wife in 93, we stay in the villa, in those apartments that were built for the Olympics. This was a few months after the Olympics. So it's remarkable to see them. Now we are in the hotel to see those places 32 years later. Okay, so as Xavier mentioned, I'm going to talk about this new great opportunity for the high temperature superconductors. And I was asked to give a talk with an introduction for a general public, what I love to do. Well, not a general public, but for scientists that are not specialized in superconductivity. So I will try to manage that line, and I would ask you to please interrupt me as many times as you want and ask me questions. And I was told that I have to stay here. I walk all the time, I'm sorry. But let's see, as I was saying, please interrupt me with any question that you may want to clarify. So this is an outline of my talk. This is essentially the more introductory, general slides about superconductivity and history and what can you do with a superconductor and what happened with it since the discovery of the HTS, and then focus a little bit more in the opportunity of the reactors. I will need to talk about a little bit of vortex physics and superconductivity, some general ideas, and then why coated conductors are so good and so unique for this possibility, and then what happens with the radiation damage and what we need to do about that. Although this is, as Xavier mentioned, kind of a history of my scientific career since I was a student, I want to emphasize the activities that I performed in the last 20 years where I work at Los Alamos National Lab, and to use the opportunity to mention the core team, my main co-workers, some of them colleagues, some postdocs that are now, I'm glad to say, all of them in good positions somewhere in the world. The main ones, okay, the core. Well, let's start. Superconductivity, as you probably all know, was discovered in Leiden in 1911 by Camerlinones, who found that the electrical resistivity of a mercury sample suddenly dropped to zero at around 4.2 Kelvin within, this is the historical plot, with transition width, let's say, of a few millikelvin. Of course, zero resistance is such a spectacular property that gave the name of superconductivity, although it's not the most fundamental property, but as we will see, but obviously it's the most spectacular. Now, the first question, when we all learned the first time about this, we made always the same question. How zero is zero? What do you mean zero? Zero is something, he has here less than 10 to the minus 5 ohms. Well, it's hard to identify with a voltmeter what is zero. But Camerlinones realized that the convincing experiment will be a persistent current experiment where you have a ring, you create a supercurrent, and the current will never decay and it stays there forever, making a magnetic moment of that ring. And he worked on that, and in a few years, I think in 1914, he managed to demonstrate and to convince the community that he had persistent currents, and consequently, he could say that the resistance was really zero. And that introduced me to the first of three important superconducting parameters, three critical parameters of a superconductor that has technological relevance. And this is the first one, that is the TC. And we will see the other two over the talk. Okay, what can you do with a superconductor? Well, the first obvious thing is, assuming that you can make wires, and we will go back to that, assuming that you can make wires, you can transport electrical power without dissipation, because the Joule dissipation is proportional to resistance zero, so you can make long transmission lines, for instance. The other thing that you can do is to make a solenoid and create a magnetic field. And if you manage to keep the solenoid in what is called persistent mode, so you close the circle, the currents will stay there in principle forever without dissipation, you can make then high magnetic fields without dissipation. And you can use it to store energy, to what is called SMES, superconducting magnetic energy storage. Of course, this was known for a very long time. The big problem was that the TC was too low, and then you have the complexity of using liquid helium and having expensive and difficult cryogenics, and that limited the applications of superconductors for a long time. It didn't preclude the applications, but made them rather limited. And then the huge thing happened in 1986. Bednorz and Müller discovered superconductivity in the range of temperatures of 30 Kelvin in an oxide, in a barium lanthanum copper oxygen system that was totally unexpected. This was very, very shaking of the scientific community, not only because the TC was higher, but also because it was going against the accepted knowledge that it was almost impossible to have TCs above 20-something Kelvin. So this was really revolutionary. And you can see that this is the plot. So this is a plot of the original paper. And this is something from this is a plot from 1988 from a conference that I went at that year. And you can see they show very spectacularly the slow improvement of TC over 70 years. And this jump of 60 or almost 100 Kelvin in a couple of years. Critical here, essential here, was the discovery of the YBCO that was at that time was just yttrium barium copper oxide by Paul Chu in 1987. And that started the high TC frenzy. In particular in my life, let me tell you, at that time I was grad student in Bariloche, working with Paco de la Cruz, as Xavier mentioned, And we learned about these materials in December 86. So we rushed to try to fabricate samples. We got our first sample in the evening of Friday, February the 13th, 1987. So we rushed to measure it. I had a squid magnetometer. I was doing my thesis in conventional superconductors, amorphous superconductors. Was okay, interesting, but nothing fascinating. So suddenly I was interested in this. We measure in our squid magnetometer. This is an attempt to see something like a Meissner effect. And so we put the sample, increased the temperature. We saw that the diamagnetism was disappearing. Then it got flat, and then we cooled down again, and we saw real expulsion of field, which is a very indicative of superconductivity. At that time, it was about midnight. We were totally excited about that. We called our boss, Paco de la Cruz. He called his colleagues, friends, including the director of the institute. They started to show up at the lab, some of them. It was a Friday night where they were at dinner with some friends, came up with a champagne with leftover of a cake. And at 2 a.m. on Saturday, we had a big party inside the laboratory. So you can see the date is already Saturday there. This is the sample, and this is my signature. And this is figure 1 of my PhD thesis. It's hard to convey the excitement at that time. After that, we were sleeping in the lab. It was a crazy time, absolutely spectacular. But it was not only us. The world got crazy with this possibility of the high temperature superconductors. And suddenly, every group that was doing anything vaguely related to condensed matter started to measure these new samples and to get grants and ask for money for these new samples and this new topic. And there were tons of publications, new meetings, dedicated conferences. It was really a big excitement and a big enthusiasm. And it was the idea that in a few years, the vision was applications will permeate every aspect of our lives. And in a few years, that will change our lives completely. And we will have all these things that are shown here. This is a recent slide, but summarizes all the ideas that already were there at that time. But then the challenges started to appear. I mean, you cool down and you start to think a little bit more. And we were mostly physicists that were fascinated with the phenomenon. But then you start to realize that there is a long way to go from having this to having a maglev. There are lots of tiny details that you should figure out if you want to have a train running at 500 kilometers an hour with 1,000 passengers inside. You want to be sure that you figure out the details. However, there was continuous progress over these almost 4 decades, strong technical progress over time. And I must say that most of the envisioned applications shown here, most of them have already been achieved. And there is a market, and there are products. And however, the market is not as huge as it was envisioned at that early time. And the question is why? Well, obviously, you're thinking about having something that is a disruptive technology, that is a worldwide change. It has to have a number of characteristics. It has to be unique. You have to think in something that cannot be done in any other way. Or if it can be done in any other way, the advantage has to be so big that it's worth to abandon the old technology and jump to the new one. Just incremental progress is not enough. Then it has to have reliability and life extension. For instance, I don't know, motors and generators, they were built, but the big non-superconducting motors have maybe efficiencies of 95%, and generators, the same thing. I'm talking about the big scale. And with superconductors, you can make efficiencies 97, 98%. Okay, it's good. In terms of megawatts, is significant, but it's not that revolutionary, not that disruptive. They have to have life extension. You want those motors to run for 30 years, 40 years. And they have to be reliable. I remember, for instance, when, wait, I remember talking a lot about fault current limiters, which exist, that has been fabricated. Fault current limiters will cut the power and preclude big damage in situations of a big storm, for instance. But then what you want is to have one of these fault current limiters operating unsupervised, alone, somewhere, doing nothing for years, because there is no need, and suddenly, in the worst storm of the season, at 3 a.m., it has to work, or else. And so reliability is a big issue. And of course, the other huge issue is the cost. These materials are still expensive, and a lot of work has been done in reducing those costs, but it is still an issue. Now, as I was saying, continuous technical progress has been done over time. So what I want to discuss today is the fact that there is now this new opportunity that is the use for making magnets for fusion reactors that appears to satisfy all of these characteristics and make it a very, very new opportunity for the ITCs, in particular for the coated conductors. So let's talk about this. Fusion reactor and magnets for what is now called compact fusion reactors. Commercial nuclear fusion power plants have been 20 years in the future since I was in my 20s. I remember discussing that in the university, and it was always there. The 20 years became a universal constant in me, and that was the joke. But now, this time, it appears to be for real. There is a lot of companies, I think that will appear later, that are now working on this. So this would have all those characteristics. The widespread access to energy produced by fusion will certainly change the world. That is clear. The other thing is that there is no other alternative. I mean, fusion reactors magnetically confused. There is another option, isn't it? That is the inertial with pushing with laser, but magnetically confined fusion requires superconductive magnets, because you need big fields in a big volume. The only way to do that is with a persistent mode, in a non-dissipative mode with a superconductor. So the standard option that has been used for decades are the low TC, for instance, niobium alloys, and this is a famous ITER system that is under construction, has been under construction for how long? Decades. That is huge. There is a person there, and uses tons and tons and tons of niobium alloys. Now, what I learned is that the reactor efficiency grows like B to the third power, like the field to the third power. Don't ask me the details. I'm not an expert in fusion, but that is what the experts tell me and publish. So there is a big push to build compact fusion reactors operating at fields of the order of 20 Tesla. That will make them smaller and consequently cheaper. Just the engineering, the building, and all the installation, and in addition to being much more efficient. And so now the plans are driven by private companies, not government. They are talking about timelines of years and not decades, and that's another big difference. So this is a huge market, and there is only one option for the coils, as I'm going to mention to you in a minute. So I was saying that you need a number of things. You need wires, you need then 3 critical parameters, and we already discussed critical temperature. Let's go to the other one. So I show you this slide, and the first thing to mention is that there has been a lot of progress since then. if we look at this, how we are now with all the hydride superconductors, we are really reaching, approaching room temperature superconductivity. However, the wires are essentially the wires built by the two materials that were discovered at the very beginning, the visco and the ones that are relevant to us that are called the second generation, the coated conductors, that are thin films of rare earth VCO coated on flexible metal tapes. And you know perfectly what I'm talking about. You're very familiar with that here. And these are the materials that could be used for these new compact magnets. So let me go a little bit of thermodynamics of superconductors. As I mentioned, zero resistance is not the most fundamental property. The most fundamental property is the Meissner effect, or perfect diamagnetism, that implies the expulsion of the magnetic field from inside a macroscopic superconductor discovered in 1933, which implies that, number one, superconductivity is a true, real thermodynamic phase transition, and consequently is the minimum free energy in some conditions of temperature and field. And second, it implies that there must exist a critical field. So there must be a phase diagram like this, where the material is superconducting below this curve and normal or non-superconducting above this curve. So this, you can see there, but it says the second property is the critical magnetic field. Then in reality, there are several critical magnetic fields. Without entering in many details, there are two types of superconductors, depending on two characteristic lengths that are the coherence length and the penetration depth. I don't have time to go in detail on that, but in the type 1 superconductors, you have this very simple phase diagram, and they are not particularly useful except for superconducting cavities, but not to make wires. And then you have type 2 superconductors. All superconducting wires are type 2, including the HTS. And in these materials, you have a much more complex phase diagram with an HC1 critical field and a upper critical field HC2, and an irreversibility line that separate two phases that contain vortices. Vortices are very interesting objects that are the center of the understanding of how superconductors operate for applications. Vortices are tubes, quantized tubes of supercurrents with an associated magnetic field. Each vortex carries one flux quantum and has a central core where the superconductivity is suppressed. And that produces a complex phase diagram with several vortex solid and vortex liquid phases. And those are the materials of our interest here. And then finally, the third concept that is important is the concept of critical current density. When you have vortices, you have a magnetic field, you have vortices in a superconductor, you apply a current, the vortices feel a force. The current exerts a force on the vortex. If the vortices move, that movement is dissipative because the core is normal and moves, and that dissipates. And that produces resistivity, kind of an ohmic resistivity. It's not ohmic in origin, but it's the same thing. And that produces the zero resistance is gone. So that is not interesting and it's not useful. However, fortunately, there is a way to avoid that. And the way to avoid that is to introduce disorder, defects in the material. These defects that are non-superconducting regions kind of attract the core of the vortex. When the vortex sits in there, the energy of the core is decreased. And so that acts as a potential energy well. And then you need to apply a finite current in order to move the vortex out of that. The vortex is pinned. And that is the whole story. The pinning of vortices is the name of the game to try to produce useful wires, because you want this critical current density JC to be as high as possible, meaning that your wire can transport as much current as possible without dissipation. So there are many types, and JC can change by orders of magnitude because it doesn't depend essentially on it depends on the material properties, but it also depends dramatically on what you put inside as disorder. So it's extrinsic. And there are many types of defects that can act as pinning centers. Some are better than others. Some are too small, some are too big. There are planar, columnar, circular, spherical, etc. So this puts all the important parameters. Now, the coated conductors, are these rare earth BCO films on flexible metal tapes, offer the best performance at high magnetic fields. So this central plot here shows the critical current density as a function of applied field for a variety of superconductors. And you can see that all the commercial low TC materials, niobium based, and so collapse at around 25 Tesla, and they become useless above a little bit less than that because you need some finite significant JC if you want to operate them. The only option are these YBCO coated conductors that can extend up to very, very high fields. So we can produce the wires. This is a plot from Superpower that used to show around 2008, where they were showing that we're growing from being able to make 1 meter of coated conductor, 1 meter, to 1 kilometer in about 7 years or 6 years or so. So they were making this progress. Now, routinely, many companies produce kilometers long tapes of YBCO. Kilometers long single pieces with all the properties that are required. How many kilometers per year? I don't want to quote a number because that changes by the day. I'm not sure, but supply may be a bottleneck. It may be more demand than offer. Now, if you are a manufacturer, that's a good problem to have. And in fact, the supply is being driven by the demand, by the fusion demand. And then let me show a particular example. This is from 2019. This is from the magnet lab in Tallahassee, in Florida, where they were able to make an insert in an existing magnet and produce above 45 Tesla with a piece of a coated conductor. So clearly you can produce huge fields that you cannot produce in any other way. Okay, so we have the wires, the TC, the HC, the JC. Let's make the fusion reactors. Now, let's build the magnets. What's the problem? The remaining big problem is radiation damage. Fusion reactors will generate very intense radiation. Essentially, the deuterium-tritium initial reaction produces 14 MeV neutrons. Those neutrons carry most of the energy that is produced. Those will be used to extract the power that you can use to heat something and produce electricity, whatever. That is the output of the reactor. But they also will produce a lot of damage. They have a very long penetration, so they will go through everything, including the coated conductors in the magnets. And they will produce a lot of secondary particles. They will heat materials and produce cascades, hit other atoms and produce many other things. Exactly what is impossible to know exactly, because that will depend on the design of the reactor, the geometry, the size, which are the materials that are the structural materials, the shielding materials that will become activated in turn. So nobody can know exactly what a reactor radiation will be unless you have an exact picture of what the reactor characteristics will be. And in compact reactors that are much smaller, this will be even worse. The radiation intensity will be higher. So what will happen with this radiation? Radiation will damage the material, and eventually the number of defects that it will produce will deteriorate the properties of the materials, particularly the coated conductor, beyond the point that they are not useful anymore. The JC will be so low that the magnet will cease to operate. So the big question is, how long will that take? Because If it takes less than a year, forget it. You cannot make a magnet per year. If it takes a century, then it's not an issue. The reality will probably be somewhere in between, in the range of a few decades. And then it's very important if 10 years or 30 years make a huge difference. And that's what we are trying to understand. So some of the radiation-induced effects will act as vortex spinning centers, and then will increase initially the JC for the reason that I explained before. May or may not, depending on the characteristics. But for sure, they will deteriorate JC at some point. There will be, so as a function of time, perhaps an initial increase, and then a deterioration, and then at some point it will go below the acceptable level. And this is what we need to understand. So the to-do list for the community is to understand radiation damage in coated conductors, particularly the deterioration at high doses. We need to understand that this disorder will interact with pre-existing defects. And then the outcome will be different depending on what are those pre-existing defects. And then the other thing that is not very well explored is that this irradiation will occur in what they call inoperando. It will be at 20 Kelvin and in the presence of a high magnetic field. I don't know if the field will be that important, but certainly the 20 Kelvin will be important. It will be different than irradiation at room temperature because of annealing effects. So for instance, what happened when the magnet has been irradiated for months or years, and then you have to warm it up for whatever reason? What happened with those defects? Annealing and the like. So a little bit of publicity. This is what I'm going to show now is essentially what I show in this conference of irradiation effects in Italy year and a half ago. Xavier was there, and this I summarized this in this review article that I just approved the final proof. So this should come out in a week or so, where all that I'm going to very quickly show you here will be expressed in much more detail. So practically, particle irradiation was a very popular activity in the early 90s. And I was very involved in that part, but it was a worldwide activity. Many groups working on that. Incident particles transfer energy to the solid in two mechanisms. The first one is direct collisions with the atoms that form the lattice. That is what is called nuclear or non-ionizing energy loss. And that is dominant for light ions, for protons, for electrons, for neutrons, up to a few MeV. And then the other option is to have very high energies, hundreds of MeV to GeV, heavy ions, and those heavy ions transfer energy in a completely different way. They transfer energy to the electronic system of the material, and they produce columnar disorder, correlated disorder. They can go, if the energy transfer is not enough, they produce kind of collection of correlated spheres of damaged material, then eventually going to discontinuous columns, then eventually to continuous columns of amorphous materials. Irradiation produces very effective pinning centers in clean YBCO single crystals, and that was mostly studied in the 1990s. So these are three examples. These are magnetization measurements. The critical current is extracted here from the width of the magnetic hysteresis using a geometrical factor. This is the critical state model. It's very well known. So the first spectacular measurement was this report. This started on day one of the high TCs, but initial measurements in polycrystalline materials were not that clear to interpret. But as soon as people had single crystals, this was a pioneer work by Vandover and co-workers at Bell Labs, 1989, where they used fast neutrons to irradiate YBCO, and they saw an increase of a factor of 100. That was spectacular. And that, in a sense, marked my future career, because my postdoc mentor, my boss, Alex Malosimov, was furious when he saw the preprint, because the IBM nemesis, the Bell Labs on the other side of the Hudson River, had completely defeated us in that. So he was furious and he wanted to do irradiations. And then is how I started to work in these proton irradiations. And we observed increases by up to 2 orders of magnitude, not with neutrons in this case, but with protons. So you have to be careful how you map. You have to know what is the DPA in one case or the other. The type of defects is different, but in both cases, what you have is randomly distributed localized effects. In this case are mostly cascade effects. In this case are small clusters, and they are very effective. Even electron irradiation that only produces Frankel pairs, point effects, is effective. Less effective, but somewhat effective. And that is because the coherence length in YBCO is so small that even point effects can act as spinning centers. So these are several examples showing the critical current density increase with irradiation. This is fast neutrons from the Vienna group. This is our own work in 3 MeV protons. So why was it useful to study single crystals? Well, first of all, because they are very clean. So they have very few defects to start with. The pre-irradiation JC is very low. So when you irradiate, anything that you see in JC is coming from what you put there controllably. So the interpretation is much easier. And in fact, a lot of vortex physics in these new materials was learned from this type of single crystal irradiations. And people were able to reach critical currents in the, including me, in the range of 20 megaamps per square centimeter at low temperature, low fields. By different methods give similar results. Then I did the experiment that was introduced directional pinning by very heavy ion irradiation, very high energy, and we produced columnar defects. And these columnar defects had the characteristic that the pinning is directional, so it's very strong when you apply the field parallel to the defects, less so when you apply the field tilted to the defects. And we showed that by measuring the hysteresis at 2 different crystallographically equivalent orientations, but one parallel and the other one not parallel to the columnar defects. So these columnar defects produce similar pinning than random particles at low temperatures and low fields, but they are better off at much better at high temperature, because they confine the whole core of the material of the vortex. Now, at the same time that the single crystals appear, the YBCO thin films started to appear. And then the question is, what happened with their JCs? Well, it soon became clear that the critical current of standard YBCO films, growing by several different methods, had critical currents that were not only high, they were higher than the best that could be achieved in single crystals, with any kind of irradiation. And that started to become obvious in around the year 2000. And these are 2 early studies, one by Bernard Damm, 1999, that one by Van der Beek in 2002, showing things in the range of 30 to 50 megaamps per square centimeter, just in films that they grow without trying to introduce any additional pinning. And that, in fact, I don't have time to go in details to this, but that was the big question in the community, a big mystery. What was the reason for the very high critical current density in YBCO films? Nobody knew at the time. In fact, if we look at what is the maximum possible current that you can produce in a superconductor, that is the depairing current, it turns out that YBCO films had the highest JC of any known superconductor, in terms of absolute values, exceeding 100 or even 150 megaamps per square centimeter, and in terms of fraction of the pairing currents. So my point always is that it's always useful, always interesting to study YBCO films and coated conductors not only for the obvious technological interest, but also for the basic science interest. So that was the beginning of the coated conductor technology and the search for methods to further improve JC at high fields and to start what is called the vortex pinning nanoengineering. And the most successful approach was the chemical introduction of second phases by chemically. And this is a pioneer work that we did, led by Judith Driscoll when she was at sabbatical at Los Alamos, introducing barium zirconate that form nanorods by self-assembly. And those nanorods act as columnar defects. So they produce very strong pinning. The nanorods were parallel to the z-axis. You have seen this sketch before, but these are nanorods produced chemically, not by heavy ion irradiation, but the physics is the same. And what we observed is that in that original study, we didn't see a big increase in self-field JC, any increase, but we saw a very strong improvement of the in-field performance that was essentially what we were looking for. This was quickly reproduced by other groups like the Yamada group, and they had this beautiful TEM showing the self-assembled nanorods. We learn, and I will not go in detail to this, but we learn to tune the growing conditions, and we learned that if we deposited the films at very high temperatures, we had essentially long and aligned nanorods. If we go to very low temperatures, kinetically, the system didn't have time to form nanorods. So they had mostly randomly distributed nanoparticles. And some intermediate temperatures, you have something splay nanorods with some distribution of angles and some nanoparticles. The remarkable observation is that this intermediate situation, what we call a mixed spinning landscape, produced the best spinning. And that turned out to be a result that is rather general. It's a mixture of defects what produces the best spinning. And that is, to a large extent, the explanation of why the critical current of the YBCO films is so high. Okay, so this is an example of processing properties correlation. The columnar growth of the PLD, these are PLD coated conductors. The columnar growth of pulse laser deposition promotes the formation of the self-assembled nanorods. Now, some people will be familiar. Pioneer work done here in 2007, showing that introduction of barium silicate could also produce very strong increase in the critical current. But in this case, not by nanorods, because nanorods didn't fall in this layer growth MOD, but instead form randomly distributed nanoparticles. So you don't see a z-axis peak here. However, the increase in the pinning is also extremely dramatic. We did similar work with work led by Masashi Miura when he was our postdoc at Los Alamos, and we introduced also nanoparticles in MOD. We show huge improvements at high temperatures, only modest improvements at low temperatures with the particles, and that was due to the fact that the nanoparticles were very large. We made systematic studies changing the chemistry and the density of the nanoparticles, and I will not talk about that because you have done everything about that at this point. And it turns out that, of course, the larger density of smaller nanoparticles, the better. So we had to go to always more nanoparticles and smaller ones. And there was a limit, and I will skip this. And but then Boris and Masashi Miura figure out a way to grow some kind of multi-layer structure and introducing barium half-nu nanoparticles that they could make even smaller, 5 times smaller in size. And then they were able to improve dramatically the critical current at low temperature. So we understand a lot of how pinning works in these materials. and how we can correlate the kind of defects that we introduce with the properties that are obtained. Now, what happens if we take one of these very high JC coated conductors and we irradiate them? Well, this is work that we did with the people at Argonne National Lab. We took some MOD samples, coated conductors from American superconductors. We irradiated with 4 MeV protons, and we observed similar to the protons that I used many years before with the single crystals, and we saw systematic increases of the critical current density with fluence. You can see here the fluence dependence at different temperatures as a function of magnetic field, and it keeps growing with higher field. Let me go quickly to this example where we wanted to show if this is also true that the mixed pinning landscapes are a general rule to improve pinning. And so in this one, we combined this 4 MeV proton irradiation. We did not do the optimum dose, a little bit less, just not to saturate. And then we introduced columnar defects by heavy ion irradiation. And by doing that, what we obtain is that the sample with columnar defects by heavy ion irradiation have a large JC increase at low fields. Then about half of the matching field, it started to decrease, and that is true at all temperatures. Then the proton irradiation produced some deterioration at self field and low fields, and then an improved with field. And the sample with both things is better than any one of them. So you take advantage of both things, this combination, this mixed pinning landscape act in cooperation to produce stronger pinning. Then we did the same irradiation, the same kind of irradiation, but with oxygen ions instead of protons. And the reason for that is that we could obtain the similar damage, measuring DPA, displacement per atom, similar level of damage with 1,000 lower doses than with the protons. So these irradiations were done in 1 second, for instance. We argue that could be useful for technological applications. So you can see here, I will not go to the detail. These are stream simulations. We try to put the Bragg peak in the center of the white VCO to maximize the damage. And then in 1 second, we could produce enhancements, you see, by a factor of 2 at 6 Tesla. Of course, we don't see orders of magnitude increase because the JC, like we have in the single crystal, because the JC here is much higher than in the single crystal to start with. But it's still a factor of 2. Manufacturers will kill for that. And then at high fields. At lower fields, we never see an improvement, and we saw a deterioration from the first dose, even from very low doses. So oxygen irradiation increases JC over most of the phase diagram and reduces it at low fields and high temperatures. And we explored that in detail. I will not have time to go in detail with this, but we took one of those samples with oxygen irradiation that shows the large increases at low fields, at high fields, low temperature, and some deterioration at low field, high temperatures. So the squares are the irradiated compared to, you can see, dropping way below the pre-irradiation value after irradiation. So our model is that the initial samples have some clusters. No, sorry, not clusters. These are nanoparticles that exist in the MOD samples and some point effects. And irradiation introduces some clusters and some more point effects. And then when we anneal, we remove some of the point effects, leaving the clusters, and that recovers the JC. Not totally, but significantly recovers the JC. At that time, we interpreted that thinking that these mixed pinning landscapes have a lot of interactions between different types of effects. Some of them are cooperative, some of them are competitive. Some combinations of effects are detrimental because they act in opposite directions. We thought that this was some kind of detrimental effect due to competition between the two types of effects. The recent understanding, motivated by the interest in the fusion community, is that this may be simply to the reduction of the superfluid density. There is a very interesting recent paper by the Vienna group discussing this. So this is an alternative recent interpretation. So I want to conclude at this point, and then there is kind of a summary. Let me go very quickly through this. Material defects are required for vortex spinning. Coated conductors have the highest JC in any known superconductors because they have many effective thrombospinning centers. The added defects are wisely optimized over 20 years to improve the highest possible JC. So there are lots of effort in many groups and companies and labs and universities in the world. Now, the radiation-induced effects in a fusion reactor will interact with the pre-existing disorder. And that initially they may or may not increase JC depending on what kind of effects they produce. And we don't know exactly what irradiations will occur in the reactor, so there are too many unknowns there. But for sure, at some point, they will start to deteriorate. And that is the part that we need to explore in more detail. This is a cartoon showing that, for instance, if we we have three different locations in the magnet where the field has different values and different orientations. So it may happen that in one of them, initially there is a very large increase. But this is not particularly good because you need the magnet to operate from day one. You cannot rely on the future increase. But anyway, it will buy you some time and eventually will start to deteriorate and go below the acceptable level. In some other location, the increase may be smaller, but deterioration will be slower. In some other case, there may be no improvement at all and a fast deterioration. The reality of this cartoon is what the community needs to figure out for each coated conductor to be used in each magnet of each fusion reactor. And I want to finish by advertising that we are having the second irradiation conference in Italy, in Gallipoli, this time in a few months, in June. The abstract submission is open till the end of this month. I'm part of the advisory committee, so I strongly encourage any one of you that is interested to take a look at the website and perhaps submit an abstract. And with that, I'm done. Thank you very much for your time.
Thank you very much for the effort to go through so many years of understanding of superconductors and the big problem of irradiation. So now, please, the talk is open for discussion or comments, questions. I'm sure that you could spend hours talking about that, but we can have a few minutes for questions. And he will be here in the afternoon and tomorrow. And of course, if any of you are interested
to talk to anyone who is interested, yes. Yes.
Just one moment. Use the microphone for.
Yeah, hello. What typical orientations do you expect to have radiation with respect to the film in nuclear fusion reactors?
Everything, because you have the tokamaks and the plasma is inside, it's a toroid inside, and that will radiate in all directions. We like to think that mostly would be in the z-axis because the plasma is inside the toroid, isn't it? But I think that then considering the shielding and considering all the secondary particles that will be produced, almost there. Oh, where is it? Here, you can see the plasma will be here and radiating in all directions, but they will be in angle also. It will go, I think you have to, that's part of the problem. You have to calculate in all possible orientations.
But maybe parallel to C is like the most prominent, no?
I think you learn a lot from parallel to C axis, particularly because if what you produce is randomly distributed, non-correlated disorder, which is mostly the case with most of the particles, particle will come here, produce, say, a cascade or a cluster. There will be some secondary particle producing this. If they are far apart, as is typically the case, they are uncorrelated. So it doesn't matter that much if the particle enters this way or this way. So if you do studies mounting your sample so the radiation comes in the proton beam, for instance, or ion beam, parallel to the z-axis, that will be very good. That will be very useful.
I have one more question, and it's regarding these experiments that you have done with different kind of particles, irradiated particles. What is the typical time of irradiation? And also in relation with fusion, what's your experience with long time radiations?
Okay, let me rephrase this. What are the fluencies or doses that will produce the optimum enhancement and then start to decrease? That's the characteristic. For protons, it was a few times 10 to the 16 protons per square centimeter. Less than 10 to the 17 protons per square centimeter started already to produce deterioration. With fast neutrons, it was 1 order of magnitude higher dose that you needed. With the oxygen, it was 3 orders of magnitude less dose, because that depends on the damage that they produce. But for instance, I remember that in our 3 MeV protons, we could do it very fast. We had to reduce, we typically minutes in irradiation, minutes. And we reduced the fluid, the flux, to avoid heating of the sample. We could have done it faster, but we were heating the sample too much. So irradiations were done in minutes, hours. 1 day of irradiation allowed you to irradiate 3, 4, 5 samples with no problem. Now, how does that translate to DPAs that you will have in a fusion reactor? That's the big question. The hope is that that will be decades.
Good luck.
Yes.
Okay, another one here.
Hi, thanks for the talk. Have you checked if there's any difference between the critical current during irradiation and afterwards?
Oh, I never did that in the old times. We didn't care. We wanted to see how JC went up. But there is a huge interest on that. I'm working now with the MIT people and working in collaboration with a student called Alexis de Vitre, who has done lots of those things. They irradiate at cryogenic temperatures with protons, and they see the evolution, and then they, without removing the sample, they anneal, they irradiate at 20 Kelvin, they anneal to 40 Kelvin and back and measure into 60 Kelvin. And then above 100 Kelvin or so, they start to see, I don't want to say wrong things, but at some point below room temperature, they start to see annealing effects. Because you see, if you have lots of Frenkel pairs, at low temperatures, they will not recombine very easily. But as you increase the kinetic energy with temperature, they will recombine. So there is a huge effort in studying that. I can find a couple of papers for you. It's mostly the MIT people and the Vienna group doing those kind of things. And the answer is yes, there are differences. There is difference in temperature, and I understand that very well. The other question that I'm less convinced is that the fact that you are passing the current has an effect in itself. And now what Alexis is doing, and I'm helping him to put magnets inside the chamber where we're doing the irradiations and try to check all those things. So temperature effect, certainly. Current effect, I'm not very convinced, but some people is very convinced that that is an effect. It's all open. Any new experiment on that will be welcome.
Thank you.
You. Any other questions, Teresa?
Hi, so congratulations also for the talk. I enjoyed a lot the history because those who, like me, that we lived that time,
Yeah.
it's very interesting to remember
Yeah.
how it happened on HTS, right? Yeah, so clearly now, what we know from irradiation damage, as you mentioned here, right, is not in an operando experiment. So clearly is that we are able to generate defects, and then we are able to see if they are correct or good or not for JC, no? But what the problem that we are facing now is how this radiation will operate, no? When we have the fusion reactor, no? And one thing that maybe is also interesting for the audience is that these compact fusion reactors are also thought to be able to exchange coils, so that they don't have to operate all the life of the reactor, but it can somehow, no? So we have to understand up to how much we can sustain the radiation damage, no? How much, and this is my question, no? How much should we interact with the people who is really designing the compact fusion reactors? Because there is also a lot of shielding coming from blankets and coming from other materials, which can help somehow, okay, in which particles we should be more concentrated or not, no? So at this moment, I would like to know in your thoughts, okay, which is the type of radiation damage that we should be focusing? So is it neutrons, or is it neutrons the easiest ones to shield by blankets? Is it alpha particles? Is it gamma, which will be, you know, so I mean, we have a lot of things to work with, okay? But which do you think is the most relevant for the application itself?
Okay, do have a couple of hours. Teresa, gamma, I would say forget it. Irradiation, the primary particles are 14.1 MeV neutrons that are very hard to produce anywhere. I'm working with the Torino people trying to do an experiment at Frascati, that they have a Frascati neutron generator that produces exactly 14.1 because it's a deuterium-tritium interaction, fusion. Problem is that the flux is miserable. So it will take years of accumulated data. When we are trying to do things. So if you have possibility to measure, that will be in all the reactors, 14.1 MeV neutrons. But then what else? It's hard to say because there will be many, many different possibilities. The other thing is that, and Mike Eiserer would argue strongly that the deterioration is rather general, rather universal. So it doesn't matter that much which particle you're using. He has to convince me of that, yeah, but it's possible. So I would say you have huge capabilities here. If you want to do something about that, is inoperando, yes, for sure, irradiations at 20 Kelvin. And large doses, start to see when it goes down, and start to see what happens when you change temperatures. And perhaps check with current. I don't bet strongly on that one, but check inoperando putting current.
Okay, thank you.
Thanks very much for the super talk. I'm a chemist and I understood most of it. I think it was super. Thank you so much.
Thank you.
I had two questions, if I may. The first one was precisely a chemistry question. You took me back to my days of being an undergraduate and studying radiochemistry and looking at radiochemistry and looking at isotope chains and all of that kind of thing. So did anyone actually do an analysis on the coated conductors after irradiation treatment to see any changes in isotope content?
I will do like a politician. I don't have the answer to that, but I have to an answer to another question, and then I will give it to you. For instance, if you in neutron experiments, a problem is the cross section of different rare earths to absorb neutrons. For instance, gadolinium. Apparently, there is one isotope of gadolinium or two that absorb very strongly. And they absorb thermal neutrons. So all experiments that are not shielded to thermal neutrons produce artifacts due to gadolinium reaction, fission probably, fission fragments, I guess, and that will not be present, they say, mostly in fusion reactors. So the Vienna people say, wrap your samples in a tantalum foil, avoid the thermal neutrons and things like that to avoid spurious results. So I know that the cross-section of some rare earths are a problem. One thing I didn't show, but I had the slide, but I didn't have the time. Some people very early on doped YBCO with uranium, and they irradiated thermal neutrons, and they produce fission, and the fission fragments of the uranium act as columnar defects. In that, rather than being, instead of being parallel, they are isotropically distributed, and they are great pinning centers also. So again, an effect of induced fission in that case.
I thought it was interesting because I was looking on the phone because I didn't remember all of the isotopes that there are in the different components. But for example, copper, you know, if you go up to copper 67, that will decompose into zinc, which I guess would be a problem for the property of the material. So it's just thinking about those kind of things. Anyway, I had another more esoteric question.
Yeah. I never hear that before. Okay,
Okay,
I
right.
have no idea.
Yeah, the other question was about, you know, I mean, these are obviously extreme conditions that, as you mentioned, that no one's done before. Is anyone actually looking at atomistic modeling of this kind of thing to see what might occur?
Modeling the damage, yes, a lot.
Yeah.
Yes, a lot of
Is there a
people.
lot of progress
Yeah.
in that area? Or?
Yes. Daniele Torsello at Torino, and I can give you a couple of references. He's my reference. It's the guy I talked to. And yes, very sophisticated modeling. And I think there is a lot to do there because they try to figure out the shape of the defects. If so I say, wow, a cluster is bubble. No, they say this kind of fractal distribution of disorder. They're sophisticated modelings, and I can put you some references, but yes, people are doing that.
Thanks very much, Leo. Thanks again.
Thank you.
Any other question or comment? So I think I agree with what Leo says, that first, that we don't have the real places to look carefully at the kind of radiation and the variety of radiation that we have. And actually, there are all around the world the interest of establishing new places of neutron sources, which are in some way adapted to what is really needed for fusion. So in particular, there is one installation that should be installed near Malaga, near Granada, actually. And I will give you some information about that. It will take time because it's unique in the world, and it's quite sophisticated to have this kind of energy of the neutrons. But then it's something that we didn't mention because it will be too long, is that these neutrons then is inducing other radiation like gammas and alphas and so on. And so we need as well to understand not only the neutrons, because for the neutrons, the experts on reactors actually are trying to shift them, but then you activate a lot of things. For instance, what he mentioned about the gadolinium, so the superconductors, coated conductors, you can use lithium, gadolinium, and whatever, but actually some of them actually cannot probably be used because there is a radiation effect.
And the 14 MeV neutrons will be everywhere, but the other particles will depend on the reactor.
And on what you have around, and so there is a lot of work on liquid metals, stainless steel, and wolframium, and so many things. And so I would say that atomic simulation is essential for sure, because we need to know exactly what's going on for the different metals. And so there is a lot of effort, not only around the world, but also here in Spain, on the metallurgical people to understand what kind of defects we have. And the superconductors are after all these metals. So we need to understand first what happens with all these metals, and at the end,
Then
the superconductors, which
superconductor.
are after that. So, but in any case, it's clear that we need to understand this. And so I think we have a lot of work to do. Okay, so if there is any other comment or question, let's thanks again, Leonardo. And any of you want to talk with him, he will be today and tomorrow around here. Thank you, Leonardo.